Okay, so we've established that f is continuous and uniformly continuous on R. Now we're going to show that it's not differentiable on R. And we just need to find one point where it's not differentiable. So can anybody propose a point where this graph, here's my absolute sine of x graph, can anybody propose a point where this won't be differentiable? 0. Okay, good. So we claim that f is not differentiable at 0. Remember, differentiable just means that that formula for f prime of c, which is a limit, doesn't exist. So in other words, i.e., the limit, remember what this says, as x goes to 0, of, well, it's f of x, which is absolute sine x, minus f of 0, which is absolute sine 0, over x minus 0, does not exist. This is really what we're saying. This is what we're claiming, right? Okay, this is just f of x minus f of c all over x minus c. We're just taking that limit there. So actually, we can simplify that. So let me just simplify it even one little step further. This is just the limit as x goes to 0, absolute sine x over x. We want to just show that that does not exist. Okay. Does somebody remember a nice way of proving that limits of functions don't exist? How do we often do that? Using sequences, right. Using sequences. And the idea is to create a sequence that of inputs that converge towards c. In this case, c is 0. But then when you look at the image of these inputs, then they're supposed to converge to the image of the function at 0, right? Of course, the image of this function doesn't actually exist at 0. We're only approaching 0 here. So we'll have to see how that plays out. In other words, our xn is converging to a point that's not in the domain of this fraction. Okay. But what would be an example of a sequence that we could consider here?
1 over x.
1 over
1 over n.
1 over n, right. 1 over n would be a great choice. Okay, 1 over n, which converges to 0. Okay, so then if we look at f of 1 over n, so I have to clarify what f, actually let's not call it f. Can I just call this thing here g of x? Let me just call that g of x. So g of 1 over n would be what? Absolute sine of 1 over n over 1 over n. Okay. And I don't need the absolute value bars on that because sine of 1 over n will be positive. So we have this sine of 1 over 1 over n. As n goes to infinity, does anybody know what that converges to?
It blows up to infinity.
I think we...
It's the same one, right? Like it's, you can do the substitution, and it's sine m over m. That's m.
This is really sine of... Yeah, this is sine of x over x.
Oh, yeah.
As x goes to 0. So sine of x looks like this, and x looks like this. So what's the ratio right here at 0 of these two functions? It's just 1. Everybody agree with that? You can also use a power series expansion of the sine function. I think I did this in an earlier review session. If you use the power series expansion of the sine function and then cancel with the denominator, you quickly can show that that is 1. So this goes to 1, right? Does that prove that this limit doesn't exist?
Yes, because x sub n converges to a value, but f of x sub n converges to different value. I mean
Well,
g.
right, so we have a sequence that converges to 0. The image of that sequence converges to something. It doesn't have to converge to... This is just like an L, right? This is like xn converging to c and g of xn converging to L. I don't see a contradiction here yet.
And butcher from the other side.
You need another sequence. That's it. You've got to come up with a different sequence because it is possible. It is possible that this limit is equal to 1 as of the work we've done so far. Based on the work we've done so far, this limit could be equal to 1 and we have no contradiction. So what Noelle is suggesting is that we consider another sequence. So if we consider, so what sequence would that be?
-1 over.
Right, -1/n, that also converges to 0. But then if we look at g of -1/n, we're going to get a fraction again, -1/n on the bottom, an absolute value of sine of -1/n on top. Of course, this minus sign comes out, but then the absolute value makes it vanish, right? So this is really the same as sine of 1/n over negative of 1/n. And what is that going to converge to as n gets large? -1. And now you have your problem. Now you have your contradiction, right? Because L cannot be both 1 and -1 at the same time. Okay, so remember that in order for this limit to exist, for every sequence that converges to C, the image of that sequence would have to converge to whatever that limit is, call it L, right? So based on the first calculation, you say, okay, L must be 1. But then based on the second calculation, you say, no, wait a minute, L must be -1. Well, it can't be both, right? Okay, so now you have a contradiction. Contradiction. So L does not exist. This limit does not exist. Because this limit does not exist, this function is not differentiable at 0. So we got that part. We got that part. Clear so far? Pretty good on that? Great. Okay, so this is reviewing the definition of a differentiable function, which we need to know. Okay, so that's that part. Now the last part, as I said, I need to correct the, I think I have it right in the solution, I just don't have the question quite right. Is this thing Riemann integrable on 0, 1? Of course on 0, 1, you actually don't even need the absolute value bars. The function is always positive, right? It's just going up like that. Okay. And it makes sense that we should be able to find this area under this graph. Remember what it means. So to say that f is Riemann integrable on an interval, it just means that the upper and lower Riemann integrals, this is getting into the material we just learned recently, these upper and lower Riemann integrals have to be the same. And remember, just to remind you here, this one right here, this is the upper Riemann integral. This is the infimum of all of the upper sums. And this one right here is the supremum of all of the lower sums. Okay, and we know that this one is always less than or equal to this one, right? But we need to know that they're actually equal to be able to argue this. So here's the thing, and I didn't quite get to this in the lecture before the break, which is kind of unfortunate. It is very hard to calculate these infimums and supremums directly because you're doing infimums and supremums over, let me just write this very clearly here, over all partitions of the interval AB. Well, how many partitions is that? That's a massive number of partitions. There's a massive number of ways of chopping up this interval into subintervals, right? Nobody is going to spend their lifetime checking every partition to calculate the upper sums and lower sums and see whether it works or not. That is really not a practical thing to do. It's not practical to calculate this one, then calculate this one, and check if they're equal. That's not practical. So we have this theorem that I asked you guys to look at, and several of you have. You guys did a great job because on the homework that I pass back, I can see that everybody's already been looking at this theorem 6.2, which is absolutely a critical result. It just says that f is Riemann integrable, and in this case the interval is 0 to 1, if and only if for all epsilon greater than 0. I'm going to prove this result on Monday for you. For this test, you don't have to know the proof. I probably will ask you to know it for the final exam, but for the third midterm, you just need to know this statement. Okay, and it is very important. So there exists a partition of, in this case, the closed interval 0, 1, with UPF minus LPF less than epsilon. This is the key. This is so much more practical. I don't have to check every partition and calculate an infimum or a supremum. All I have to do is find one partition that makes the UPF and the LPF close to each other. That's all I have to do. So this is much, much more practical. Now, here is the thing about this particular example. This is the secret to this. This function, so I don't know what partition to use yet. I don't know what partition I want to use, but I will tell you this. This function is an increasing function. Because it's increasing, so you remember how the UPFs are calculated? The UPFs are, you know, these capital MI's times delta XI's over some set of terms, right? And the LPFs are the same exact sum with these little mi's times delta xi's. When you subtract them, which is what we need to do here, when you subtract them, of course, let's see what we're going to get, UPF minus LPF, we're going to get a summation, n terms, of big MI minus little mi times delta xi. Right? You're really just subtracting term by term. Here's the thing though. Because this is increasing, increasing function, right? So the big M1 is this value right here. And the big M2 is this value. And the big M3 is this value. And the big M4 is this value. They're all the right-hand endpoints. But the little m values are going to be all of these left-hand endpoints. Agreed? Which are basically, in other words, what we're saying is that one of the big MI's is always the same as one of the little MI's. Now these delta XI's, they could vary. They might depend on where, like you can see here, I didn't make my intervals the same width. But I could choose a partition where they were all the same.
So you're going to have like
exactly
a bunch
what
of
you want.
cancellations?
Pardon me?
You're going to have a bunch of cancellations?
Correct. You're going to get a bunch, when you subtract we want to set this up so that we get lots of cancellations. Okay, so what I'm going to suggest you do, here's the way to do this. I think I did do this in class. We did an example of this in class. We let P sub n be the partition into n equal pieces, right? Okay, so this is the partition equal the partition with n subintervals of width b minus a over n, which in this case is 1 minus 0 over n. So all of the delta xi's, these are all of the delta xi's. They're all just 1 over n. So u of Pnf minus L of Pnf, if we subtract these guys. Here's my formula right here. In this formula, all of the delta xi's are the same number. They're all just 1 over n. I'm going to factor that out therefore. And then what am I left adding up here? What do I have left to add up? I'm just going to erase this little piece right here. What do I have left to add up? Well, I have to add up big M1 minus little m1. I'm just going to write that down. And then add to that big M2 minus little m2. plus dot 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 plus big Mn minus little mn. Really, you see the UPF and the LPF here. All of the delta xi's have been factored out as the same number for each subinterval, right? Our subintervals are equally spaced. That's what we're doing. So every single one of these intervals, delta xi is just of width b minus a over n. But now the point that we were just making, guys, is that big M1 is the same as what? Little m2. Big M1 is the same, right? That's this value here. Big M1, the maximum on the first subinterval, is the same as the minimum on the second subinterval. And then the maximum on the second subinterval will be the same as the minimum on the third subinterval. Right? And all the way along the line, they're all going to cancel out except for the very biggest number and the very smallest number. Which in this case, by the way, little m1 is equal to what? 0. Sine of 0, which is 0. And big Mn is equal to what?
1.
Sine of 1. It's sine of 1, right? So this is just the sine of 1. Exactly, right. That's it, guys. Given an epsilon greater than 0, do you think you could make a partition such that this difference would be less than epsilon? Right? You want this difference to be less than epsilon? You just have to choose n big enough. Right? So let's write down the proof now. It's a really simple proof. Okay? It's a very nice proof. Okay, so this, by the way, this is a huge important thing. This idea of equal spaced partition with equal spacing is really, really important. Okay, so here's the idea. Let epsilon greater than 0 be given. This is actually now the proof. After all of that background, we can now do the proof. Choose n in the natural numbers with 1 over n times the sine of 1 less than epsilon. We can definitely do that. Okay. Then, as per the calculation above, over here kind of our scratch work, from the calculation above, u of Pnf minus L of Pnf, right, is equal to 1 over n times the sine of 1 is less than epsilon. Okay, great. So f is Riemann integrable on 0, 1 by theorem 6.2. Absolutely the easiest way to prove that. You don't want to do it from the definitions of these things. You want to use this theorem. This is one of the most important, this is probably the most important theorem in chapter 6. Okay, you're going to use this thing a million times. Because you don't have to look at every partition. You just have to make one good partition that works for you. You never really figure out what n is, but that's okay. You wouldn't expect to figure out what n is because it's going to depend on what epsilon is. Somebody hands you the epsilon first, and then you find the n from there. Question, yeah?
So when is it not okay to have Pn, to have n subintervals of with b minus a over n?
When is it not okay to do that?
Yeah.
Oh, it's always okay to choose that.
Okay, so then that makes every problem really easy, right?
Well, I wish that's true. Now, this is an increasing function,
Oh, okay.
which allowed us to get all this cancellation, right? You don't always get all of that cancellation to work out. So, you have to be a little careful.
Right.
If it's like increasing, or if it's like piecewise, like piecewise harmonic, right? Then
Yeah,
you
what
can
if your
say-
graph did something like that?
Right.
What you can do, we're going to prove this later, is that if f is Riemann integrable on AB, on an interval AB, and it's Riemann integrable on an interval BC, then it's actually Riemann integrable on the whole interval AC. So you can chop your function up into monotonic sections and do this trick. Exactly right. We're gonna come to this in more formality later on.
Isn't
Actually,
that like kind of one of our armor problems?
probably. I can't quite remember off the top of my head what all the more problems were. But I believe it probably was.
Yeah.
Yeah. Okay. Yeah. It's probably one of your. Okay. So you guys are gonna do that, and then you'll be able to use it. Okay. Everybody okay with this? Okay, we've been here a while and we've done 2 problems, but I think we've done two of the longer ones. Let's go back to so I've done the first and last problem on the handout. Now let's start working our way through the middle, the questions that are in the middle a little bit. See what we can do with some of those. Everybody hanging in there okay? I know it's kind of hard. Been on break for a while. Have to start thinking about hard things again. Some of us didn't get much sleep last night, myself included. All right, we'll see. Maybe these won't go. I think the rest of these are going to go a little easier, or at least some of these are going to go a lot easier. So let's look at number 2. I don't think this one's too bad. It says, give an example. It says draw an example. It doesn't even ask you for a formula. It just says draw an example of a function. There's going to be an interval a,b, and they want a function f. And it's supposed to be Riemann integrable. Okay, so we need a Riemann integrable function. And we want u of P3f to be better than u of P4f for estimating the integral of f from a to b. Now, this UP3, this P3 thing again, that's that same thing. So here's AB. We're chopping the interval into 3 parts. Or we could chop the interval into 4 parts. Right? So this is P3 and this is P4, partition-wise. 3 sections versus 4 sections. Now, your intuition from calculus should be that, well, the more I chop my interval into smaller and smaller pieces, the better the estimate should be. So your intuition should be that P4 would give you a better estimate for the integral than P3. This problem is asking you to show that it's not necessarily true. That you can actually have a function where the upper sum, at least for the upper sum, with 3 subintervals is better than the upper sum with 4 subintervals. Remember, guys, this is just simply m1 delta x1. Well, actually, remember that all of the delta x's are just going to be b minus a, in this case, over 3. Big M1 plus big M2 plus big M3. That's what that is, right? So, can somebody give me an